Okay, hello. Last talk of the day. You've almost made it. I'm going to talk about type parameters and type members. I'm going to ask a quick question. Who has used both type parameters and type members somewhere in Scala code? Who has used only one or the other? There's like hands which are almost going up, which like you're not confident about admitting to it. But so Scala does have these two different ways of dealing with what's a very similar concept. And in the 10 years or so that I've been programming Scala, I've been aware, obviously, that both of these features are available. And until I started preparing this talk, I was never really sure about the reasons why I wanted to use one or the other. My experience evolved over those years I was learning Scala to get some sort of intuition, but I never really had a formal understanding of why one or the other is better for certain circumstances. So let's get started. You're probably very familiar with something like this. It's a type with a type parameter. You all know list. You all know int. Nothing special. And this is what it looks like in usage. We have a very simple value called xs, which is of type list of int, and there's the value. Nothing too scary yet. And this is a simplified version of the definition of that list. Now, we could have implemented that, or the designers of Scala could have implemented that with a type member instead. Let's call it mlist for member list. This is a little bit different. We don't have the type parameter anymore, and we have to specify type and give it a name. Now, if you wanted to write down that type, or the equivalent of the type we saw before, you would write it like this. You maybe haven't seen this before with the bubble on the right-hand side, the type refinement, where we're specifying that the element type is int. But this is basically equivalent to list of int, as we saw before. You're probably more familiar with writing the type in this form, where you just don't bother with that refinement. But that's effectively the same as saying, well, we don't care about the parameter. We don't care about that inner type value. And if we were writing the same type with the same specificity with type parameters, this is what we'd write. We'd have list of underscore, which is equivalent to list of t for some type t, some unspecified type t. So it's an existential. Who's happy and comfortable with existentials here? That's very few people. Okay. I'm sure they're not that complicated, but they're one of the kinds of types in Scala that you hopefully don't see too often. And I think that underscore in list will probably make you feel a little bit uncomfortable, because it feels like there's something wrong there where we're sort of omitting that type information which we'd normally have. But we can actually write all of these, all combinations of parameters and members and universal and existential. So where the type is fully specified, that's universal. That's universally universally quantified as a type, which means everywhere we know everywhere that's specified, we know what that inner type is. And I don't know if you can see the cursor there. You'll notice something about these two ways of writing existential member types and universal parameter types. They're shorter than the other two options. So the syntax in Scala is very much biased towards writing parameters universally quantified and writing type members existentially quantified. So this is really important. If we wanted to universally quantify a member or existentially quantify a parameter, we would have to write one of these two options here, which, I mean, they're just long and cumbersome. It's really not what we want to be writing, at least not frequently in Scala code. But you can do everything. You can write all of these, all combinations of of these things. You can even, I don't know if anyone recognises what I've written here. Anyone? This is the same thing. Did I hear an F? It was the F-bounded polymorphism. If you've ever seen this before, this is kind of a bit like a recursive type parameter here. We can write that as a type member if we really want to. We need all this stuff here, but it's completely possible and it works in basically the same way. It's just that this is a very strong case for suggesting that a type parameter would be more appropriate than a type member. So I had some speaker notes actually, which were meant to tell me why I was showing all of these slides, but I've long since departed from this script. So yeah, anyway. So if we had an instance of an mlist here, our member list, this is our mocked up type member version of a list, and we give that the type mlist, we've all of a sudden lost all of the information we knew about the type member, which we can see on the right hand side is int. It's an mlist of ints, but as soon as we ascribe this type here, mlist, without the refinement, we've lost that information, and we can never gain that back unless we artificially cast to the type again. And the same thing in type parameter form would look like this, and we have this big hint that something's being lost by this underscore you can see here. But here's an example where that doesn't matter. If we had a method which was basically just getting the length of a list, we're not actually using any information from the type parameter here. So we can call this method with a list of ints, list of strings, but the return type is int. It doesn't matter what the type is, so we can very safely and very comfortably ignore it. We can make this an existential, and we have this choice as to whether we make a parameter, whether we make an inner type a parameter or a member. And it's cases like this that sort of indicate to us which we think is the more appropriate solution. If we're frequently finding we're calling, we're referring to a type hiding or deliberately forgetting the information of the inner type, then that's maybe an indication it should be a type member. If we're frequently needing to add the refinement to our type members, to our types with the type members to specify what that type is, that's probably an indication that it should maybe be a parameter. But in all cases, you have the alternative. You can always write it the other way if you want to. And an indication as to how frequently you'll need to go one way or the other is how much of the API, how much of the public API of that type exposes the inner type here. Now, this is sort of the exceptional case where we've got a list which has a lot of methods that do refer to the type, like just the apply method. You get a value from it, or the head method. It uses the type of the list in the return type of that method call. But this exceptional case, we have length, which doesn't refer to it at all. It always consistently returns int. So it's a matter of judging. It's a matter of judgment as to how much of the API you think needs to track that type and how much doesn't. And I mean, there's various reasons why you might want to forget information. I'm going to show you an example here. This is a little a toy type class. I'll let you glance at this for a second. This is a type class for joining a collection of things from one type into another type. So joining a collection of characters into a string, for example. I'm not going to show you any implementations, but it's called a joiner. It takes an element, which would be the sort of the character type, and I've implemented it with a return type R, also the return type R, which I've chosen to use the type member for. And it's only got one useful method, join, which takes a sequence of elements, so maybe characters, and returns a string or whatever is appropriate. And we might use that joiner in a method like this. So we call this method, we pass it some characters, and the compiler will go off and look for an implicit. And it will find an implicit like this one. So maybe we've got a character joiner somewhere in scope. And the type of that is joiner for characters where the return type is string. Is that okay? Is everyone sort of sufficiently familiar with type classes or the vague idea to appreciate that? Now, can anyone tell me what the type of J is? Sorry, say that louder.
Joiner of T for some type R.
No. So assuming it's been resolved, Miles, you put your hand up. Go on. So there's a couple of possible answers, and okay. So the compiler knows a little bit more than maybe you realise within the signature of this method. So you might look at this and think, J, well, the type is obviously joiner of T. I mean, it says joiner of T there. But the compiler knows a bit more than that. It knows that the type is more specifically J.type. It knows exactly which implicit gets resolved, and I'm going to tell you it's this one, and it knows that the type of J is joiner of character with the refinement of R equals string. So it knows a more specific type within the body, within that method signature. So what the compiler actually knows is something like this, and excuse the formatting, which isn't great, but it means that for this method here, we can actually refer to j.r, and the compiler will know, by virtue of the implicit that's resolved, that r is string and that the return type resolves to string. Now this is a really subtle feature of Scala, but it's actually quite fundamental to a lot of things working as well as they do. And then we just call j.join, and that will return the j.r type, which we know is string. Does that make at least some sense, even if you've maybe not encountered this exact situation before? Okay, now if we were to write the same thing with type parameters, we might have two parameters. We've got element, and then we've promoted the R type, the return type, to a parameter now. And again, we're returning R. But we have to rewrite our doJoin method. We have to add this R in here. We've now, well, in order to have this R, to pass it from the parameter here to the return type, we need to track it through the method signature. And in order to do that, we need to mention it. We need to define that there is an R that is being tracked through here in order to be able to return it here. Now, what this means is that it's sort of polluting the method signature a little bit. And consequently, if we wanted to call doJoin explicitly specifying the type T, we have no option but to specify R as well. Whereas R, we would actually much prefer to be inferred. So this is a, I mean, again, it's quite a subtle case, but it's a clear case where a type member is actually a better solution than a type parameter. So I want to talk, I don't know how I'm doing for time, but I wanted to talk a little bit about variance. So this is one big difference between type members and type parameters. Oh, Dan, what, seriously? What is it? No, go on.
I was just going to say that, there's also certain things that simply will not infer, will not type check at all if you try to do them as a second type member rather than as a type member in the sorts of type classes that we were just describing.
Right.
It's not just a syntax thing. Some things will actually not compute.
Okay, I believe you. I'm sure I've seen examples of this. I'd be interested to have an example next time I give the talk. But if the video or anyone else didn't hear that, Daniel's saying that actually it's more than it's more than just the annoyance of having to specify that R. It's that we sometimes can't even write the type R, or that it.
So sometimes, even if you're not trying to explicitly specify R, like you're still relying on type inference.
Yeah.
Sometimes the compiler simply cannot compute an R if it's in a type parameter position, whereas it can compute it in the.
Right. So sometimes the compiler simply can't compute the R when it's in a type parameter position. Whereas it can when it's a type member that's referred to as a path to that type. Thank you. That's an even better reason than the reason I had that slide in there for. So variance is one big area where type members and type parameters differ, and type parameters can have variance annotations. They can have a plus or a minus on the parameter. Now that. It's not true to say that type members don't have variance. They do, but they don't have definition site variance. So, why do I? There we are. So, just to quickly, have I missed a slide? No. Just to quickly recap, if you have a covariant type, we've got trait cov covariant, which is covariant in its parameter a. We know that we can say that actually that plus isn't meant to be there. We know that a cov of runtime exception is a subtype of cov of exception simply by virtue of it being covariant and runtime exception being a subtype of exception. You can think of this, if you like, as the subtyping or supertyping relationship between the parameters being promoted to the outer types as well by virtue of the covariance. And the arrow goes the other way if it's contravariant, but that's a longer discussion. But what happens here? If we try and convert that to type members, we have no way of specifying this type to be covariant or contravariant. So what is the relationship between these two types? What are these question marks? Is it subtyping? Is it supertyping? Is it equality? Well, actually, there's no relation between these types, because when we use an equal sign here, this is invariance, and a foo with t equal to runtime exception, even though there's a relationship between runtime exception and exception, there is no we can't infer any relationship between foo of those things. So that there is no solution to this. What we can do is we can define a subtyping relationship. So we can say T is a subtype of runtime exception, and T is a subtype of exception, and then the inequality or the type inequality holds. So this is equivalent to covariance, but this is use site covariance. When I say use site, I mean the site at which you write the type down, and this also actually Miles and I looked at this yesterday, and the same thing works for contravariance. We can turn this arrow the other way around, and this arrow will change the other way around as well. This becomes obviously a lower bound then. So it works as you might hope, and maybe not as you might expect, but as you might hope it to. So we can one last thing we can do is we can actually convert that. We can convert use site variance to type parameters. So we can actually define this same subtyping relationship for an invariant type with a type parameter, provided we write, provided we specify at the use site that our type is a subtype of runtime exception, and consequently, and also a subtype of exception. Then that will hold. So there is equivalence between type members and type parameters for use site variance. For definition site variance, that's only available with annotations for type parameters. So why don't type members have variance? Well, the benefit we get, which is probably part of a maybe a longer talk, and maybe it's not even worthy of talking about too much because it's not that useful, is that we can defer a lot of the checks that get done at the definition site. We can defer them until the point where the value is instantiated with type members. So that is what we gain. We can write code with type members that aren't constrained by any variance that we wouldn't be able to write with variant type parameters. So to summarize some of these points. By default, type members are existential when you write the type down, and conversely, type parameters are universally quantified. But because they're universally quantified, we always have to track them, and that's sometimes a disadvantage. And using types with parameters means we sometimes need to introduce parameters to methods which use those types in order to track them across the signature. And as Daniel pointed out, that actually causes more problems because it means we can't actually infer them and use those types in all cases. Type parameters support definition site variance, whereas that was my last point. Whereas well, the additional point I was going to make is that whereas both type parameters and type members support use site variance. But they are very, very similar. They are interchangeable in most cases. You will probably find yourself refactoring code between one and the other when you encounter one of the little esoteric cases that I've mentioned here, or possibly others I haven't mentioned. So largely it doesn't matter too much. But I still, having gone through the process of trying to formalize this and trying to understand the logic I use to decide which is most appropriate, I still can't come up with a better reason or better explanation than to say it's still the one that feels right most of the time. And you have to work with them. You have to practice using them to gain some sort of intuition. And it's probably the most disappointing climax to both a talk and a conference. But but the answer is do what feels right. And I'm going to say, first of all, thank you for listening. But before we move on, I'd like to also thank Adalbert. Is he still here? He very kindly, well, both he and I submitted basically the same talk for this conference. And he kindly stepped aside and allowed me to give it. I hope I've done it justice. The other person who's not here I'd like to thank is Stephen Kompel, who wrote a really brilliant series of blogs on typelevel.org. They go beyond anything I've discussed here by an order of magnitude. I can recommend reading them and just spending time trying to understand the details. I think he did six or seven articles. 8. Okay, so there's. Yeah, well worth reading. So at that point, I will say, do you have any questions?